Section 7.1, Right Triangle Trigonometry and Applications. If I know that the point here is xy, for any circle we get the following definitions. Sine is the same thing as y divided by r. Cosine is x divided by r. Tangent is y divided by x. Cosecant is the reciprocal of sine, or r divided by y. Secant is the reciprocal of cosine, or r divided by x. Cotangent is the reciprocal of tangent, or x divided by r. Well, then what happens is this. Well, instead of using that r radius, we just superimpose a right triangle. And so specifically, we're restricting ourselves to acute triangles. Acute, remember, acute angles is one that is less than 90 degrees, or that's the same thing as pi halves, right? And so all of our thetas that we're considering about in right triangles are going to be values smaller than 90 degrees. Okay, as long as all that's true, then given this angle theta here, then what happens is we're going to have a couple sides listed. Well, of course, this is a right triangle, and since it's a right triangle, it has a hypotenuse, okay? The hypotenuse is always the side opposite the right angle. Then we have two other sides to deal with, and that is the side opposite the angle we're talking about. And so once we've decided on which angle is theta, opposite side is opposite theta. And if there's an opposite side of theta, there's an adjacent side to theta. That's the one that touches theta. So once we have these definitions, recognize that all of this is exactly what we've already talked about in terms of our circle definitions. Our hypotenuse is r. Our opposite side is really going to be in terms of the y value, and our adjacent side is really going to be the x value. And so all of our definitions end up lining up, but sine of theta is then going to be specifically the opposite over the hypotenuse. The cosine of theta is then going to be the adjacent over the hypotenuse. Tangent of theta is then going to be the opposite over the adjacent. Cosecant is then going to be the hypotenuse over the opposite side. Secant is going to be the hypotenuse over the adjacent side. And cotangent is going to be the adjacent over the opposite side. Now, often enough, this triangle representation, these definitions are noticed exactly the same as our circle definitions. We've just limited ourselves to only working with acute angles. But some people will use the mnemonic to help you remember the sine, cosine, tangent in terms of a triangle as SOHCAHTOA. And so if SOHCAHTOA helps you remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, then great. But you need these definitions in addition to our circle definitions. Alright, so once we have all that, we're just going to solve triangles. Given right triangles, this one specifically, we want to find the exact value of all 6 trigonometric functions of the angle theta. Notice that they've already marked theta for us. Now we do have a problem. Specifically, we're missing a side. And just to get us on track, if theta is this angle, of course the side opposite the triangle is always the hypotenuse, and the side opposite the angle theta is the opposite side. So really the only one that's left for us to find is the adjacent side, and so the adjacent side is this unknown here. But how can I find it? Well, if I have a right triangle, then I have Pythagorean theorem. That's going to be a squared plus 7 squared is equal to 10 squared. So that's going to give me that a squared is equal to 100 minus 49. And 100 minus 49 is 51. And so I get that a squared is equal to 51, which if I take the square root of both sides, well, that's then going to give me that a is equal to root 51. Root 51 has a prime factorization of 3 times 17, so it won't simplify any further. So then I get that a is equal to root 51. At this point, I can find sine of theta, cosine of theta, tangent of theta. I recall that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Thus, this is 7 divided by 10. Cosine of theta is going to be root 51 divided by 10. And tangent of theta is going to be 7 divided by root 51. If for some reason we have to rationalize, you could rationalize, but that's just going to be 7 root 51 over 50. Well then, if that's the case, if I want to find cosecant of theta, secant of theta, cotangent of theta, you could use the formal definitions, or you can of course find the reciprocals, which is then going to be 10/7, 10 over root 51. If for some reason we need to rationalize, that's of course the same thing as 10 root 51 divided by 51. And cotangent of theta is then going to be root 51 over 7. And so we found the exact value of all 6 trigonometric functions for this specific triangle. Well, now we want to play a game. We want to find the ratios of the given figure. And so notice that here we have a, b's, and c's representing lowercase a, b's, and c's representing the side lengths, and a and b representing angle measurements. And so a and b are angle measurements. And so if I want to find what is sine of b is going to be the opposite over the hypotenuse, or little b divided by c. Well, if I want to find cosine of b, cosine of big B is going to be the adjacent over the hypotenuse. That's going to be a divided by c. Sine of a, well, that's going to be opposite over hypotenuse, and that's going to be a divided by c. And cosine of big A is specifically going to be the adjacent over the hypotenuse, so b divided by c. Now, what we're supposed to recognize at this point is that there's some equivalences here. And so notice that sine of A is the same thing as cosine of B. And there's a reason for this. Specifically, A and B are complementary angles. Now, what do I mean when I say complementary? I mean that if you add those two angles up, you're going to get a total of 90 degrees, or pi halves, of the angle measurement. Now, how do we know all that? We know all that because if you have any triangle and you add all the angle measurements in a triangle up, you're going to get 180 degrees. And since specifically I have a 90 degree angle, 180 minus 90 leaves me with 90, and so the two acute angles in a right triangle are always complementary angles. And so once again, notice that if I take sine of A, that's the same thing as cosine of B if those two angles are complementary. So A and B are complementary, and we're seeing that there's this equivalence that occurs. Well, not only do we get that equivalence, but we also get the fact that sine of B, being B over C, is the same thing as cosine of A, right? So 1 is equal to 4, and 3 is equal to 2. Sine of big B is equal to cosine of A, and cosine of B is equal to sine of A. The beauty of noticing that the complementary angles of sine and cosine are being equal gives rise to this co-function identities that I mentioned previously. These things are also going to be called the complementary angle theorem. And so let's just state them. Specifically, sine of 90 degrees minus theta is going to be equal to cosine of theta. Now, this is just because we're using the definition of complementary. 90 degrees minus some angle gives us cosine. Exactly the same way, cosine of 90 degrees minus theta is going to give us sine of theta. Now, these are the only ones I've listed on your handout because once you have sine and cosine, you can, of course, use the quotient identities and the reciprocal identities to get all the other ones. But I'm going to list them here for you. Specifically, sine divided by cosine of 90 degrees minus theta, that is tangent of 90 degrees minus theta, is cotangent of theta. Or you can find cotangent of 90 degrees minus theta is tangent of theta. Secant of 90 degrees minus theta, that's going to be equal to cosecant of theta. And cosecant of 90 degrees minus theta is going to be equal to secant of theta. And so once again, like I said, all you really have to do is use these first two, and you can get all the other ones for free. Now, once again, you can also verify these cofunction identities by using the sum or difference identities that we talked about previous. So now what we want to do is we want to use the complementary angle theorem to rewrite the following. And so specifically, I'm trying to write them in terms of their cofunction. And so sine of 35 degrees is really the exact same thing as cosine of 90 degrees minus 35 degrees. And so I claim that sine of 35 degrees is exactly the same as saying cosine of 55 degrees. That's the complementary angle theorem or the cofunction identity. They're the same. All right, well then if I've got tangent of pi thirds, I claim that tangent of pi thirds is the same thing as cotangent of 90 degrees in radians is pi halves minus pi thirds. And so pi halves minus pi thirds, finding a common denominator, that's going to be multiply by 1 in disguise, multiply by 1 in disguise. I get that this is 3 pi sixth minus 2 pi sixth. 3 pi minus 2 pi, that's going to be pi sixth. And so I claim that tangent of pi thirds is the exact same thing as cotangent of pi sixth. Secant of pi twelfths. Secant of pi twelfth is going to be the exact same thing as cosecant of pi halves minus pi twelfths. And so pi halves minus pi twelfths, multiply by 1 in disguise, that's going to give me 5 pi twelfths. And so I claim that's the same thing as cosecant of 5 pi twelfths. Now let's say that we want to use the complementary angle theorem to find the exact value of the following. And so if I have sine of 58 degrees minus cosine of 32 degrees, what's really happening here? Well, if you want, what's good to recognize is that 58 degrees plus 32 degrees is 90 degrees, which means that 58 and 32 degrees are complementary, which means that I can play a trick here. I can rewrite this as sine of 58 degrees. I'm going to leave that one alone, minus this is the same thing as sine of 90 degrees minus 32 degrees. But that's the exact same thing as sine of 58 degrees. And so sine of 58 degrees minus sine of 58 degrees, that's just 0. There we are. That's our exact solution. Let's try another. Here we have 1 minus cosine squared of 55 degrees minus cosine squared of 35 degrees. Well, let's play another trick. Recognize that 55 degrees plus 35 degrees, that's 90 degrees again. So that means 35 and 55 are complementary. Well, if that's the case, then I can think about the fact that, and if you just square our cofunction identities or our complementary angle theorems, whichever you want to call them, that's going to give me that cosine squared of 35 degrees is the exact same thing as sine squared of 90 degrees minus 35 degrees. But 90 degrees minus 35 degrees is just going to be 55 degrees. So that's sine squared of 55 degrees. Okay, well let's plug that in and rewrite this. This is then 1 minus cosine squared of 55 degrees minus sine squared of 55 degrees. At this point, if we're trying to figure out what in the world could we do further, I notice these two negatives here. And I'm going to treat those as the greatest common factor, and so I'm going to factor that negative out. This is then 1 minus cosine squared of 55 degrees plus sine squared of 55 degrees. But at this point, cosine squared plus sine squared of the same angle value, that's 1. Pythagorean identity tells me that this is 1 minus 1. Well, 1 minus 1 is 0. There we are. We're finished. So now we want to solve the right triangle. We want to round the lengths of the sides to 2 decimal places and the angle measure to 1 decimal place if necessary. And so let's actually first find our missing angle measurement, B. Well, what's B going to be? Well, remember that since we have a right triangle, I know that 35 degrees in B must be complementary. Complementary meaning they add up to be 90 degrees. So B must be 90 degrees minus 35 degrees. Thus, B is equal to 55 degrees, and there was no need to do any rounding. B is 55 degrees. Well, then I need to find the side length A and the side length C. Well, I remember that my A, we just need to pick one of these angles. Personally, I'm going to choose to work with 35 degrees because it's the given. just in case I made a mistake on B, my mistakes won't compound. And so what I'm going to do is I'm going to recognize that with relation to 35 degrees, if this is my angle theta that I'm going to work with, A is really my opposite side. Okay? And C is, of course, the hypotenuse because it's opposite the right angle. Well, if I'm thinking about opposite with relation to adjacent, because of course this is my adjacent side to 35, adjacent and opposite have the direct relation of tangent. And so I remember that tangent of theta is really equal to the opposite side over the adjacent side. But in terms of my picture, if I take tangent of theta where theta is 35 degrees, and then that's equal to the opposite side, A, that I don't know what it is, over the adjacent side, 8, then I can actually multiply both sides by 8, and I get that A is equal to 8 tangent of 35 degrees. Don't forget to make sure that you're in the correct degree or radian mode. This time we need to be in degrees. Then 8 times the tangent of 35, since we are rounding side measurements to 2 decimal places, I claim that this is approximately 5.60. And so I claim that A is equal to 5.60. Approximately, of course we are rounding. Well, then I need to find that hypotenuse C. Once again, I'm going to base everything off of the things that I were given originally if I can, and so I want to use the adjacent and the hypotenuse. And so I then recall that if I'm relating adjacent and hypotenuse, that's going to be the cosine function. And so I then remember that cosine of theta is the same thing as the adjacent divided by the hypotenuse, which in terms of if theta is 35 degrees, that says that cosine of 35 degrees is then going to be equal to 8 divided by that unknown C value. Well then, what can we do? Well, I need to solve for C. So if I multiply both sides by C, then I get that C times cosine of 35 degrees is equal to 8. Well, then I can divide by that value cosine of 35 degrees, divide by cosine of 35 degrees. I then get that C is equal to 8 divided by cosine of 35 degrees. And so then I can evaluate this. 8 divided by cosine of 35 degrees. Of course, make sure you're in degree mode at this point. And I get the approximate value of 9.77. And so I claim that the hypotenuse that we have found is 9.77. And so we have found all of the values that we needed to find. Let's try another. Recognize that in this problem, I don't have either of the acute angles. I also don't have the hypotenuse C, and so I remember that this is a hypotenuse. But I can use the Pythagorean theorem to find that hypotenuse. So specifically, 7 squared plus 4 squared is equal to that C squared. So that's 49 plus 16 is equal to C squared. So I get 65 is equal to C squared. Take the square root of both sides. We're working with a right triangle, so it's always going to be positive. And C is then equal to root 65. But 65 is 5 times 13, and since both of those are prime, that won't reduce, and so I claim my hypotenuse is root 65. Now at this point, I just need to find my angles A and my angles B. How in the world can we do this? I claim that if we pretend that A is theta, then what can we do? If A is theta, I can consider the trig function. Tangent of theta is then going to be equal to the opposite over the adjacent side. And so if it's the opposite side over the adjacent side, opposite theta is 4. Adjacent side is 7. And so that means that tangent of my unknown capital A is then also equal to 4 divided by 7. Now at this point, we're just solving trigonometric equations. And so what can we do to undo tangent? Well, we can take tangent inverse of both sides. And so then I get that A is equal to tangent inverse of 4/7. Now nobody's told us to be in degrees or radians, so I'm going to continue to remain in degrees. And since we're rounding angle measurements to 1 decimal place, I claim that the tangent inverse of 4/7 is really 29.7 degrees. Okay, well if you wanted, you could use the tangent of B is equal to 7 divided by 4 and do the same thing, or you can just use the fact that we know that A and B must be complementary, and therefore angle B must be equal to 90 degrees minus 29.7 degrees, and I get that B, and remember, since I technically approximated, this is also an approximation. It's just already taken care of for me. And so I get that 60.3 degrees. And so I've now found that A is 29.7 degrees, B is 60.3 degrees, and C side length is root 65. And at this point, I guess they did say round the lengths of the sides to do decimal places, so let's actually round that to 2 decimal places. But the square root of 65 is approximately 8.06, and so I guess that's really what they wanted. Alright, an application problem. A surveyor can measure the width of a river by setting up a transit at point C on one side of the river and taking a siding of a point A on the other side. Given the figure, after turning through an angle of 90 degrees, so the surveyor was looking here, and then they rotated to here to give us 90 degrees, okay, but that's all in our figure. The surveyor then walks a distance of 300 meters to a point B. So I'm just going to label things that I get. Using the transit at point B, the angle theta is measured between point C and A to be 25 degrees. What is the width of the river rounded to the nearest meter? And so nearest meter is going to be rounded to the nearest meter. So we're going to round to a whole number. Alright, so what do we have here? Well, I have an angle theta. Well, angle theta, this is going to be opposite. This is going to be adjacent. I remember that the trig function that's opposite and adjacent is either tangent or cotangent. So I'm going to say, well, tangent of 25 degrees is equal to the opposite side, B, divided by the adjacent side, 300. Then I can solve for B, multiply both sides by 300. I get that B is then equal to 300 tangent of 25 degrees, double checking that you're in degree mode, 300 times tangent of 25, I get that B is approximately, rounded to the nearest meter, 140 meters. I got 139.8, and so rounded to the nearest meter, there we are. Now, some application problems. The deal is that when we're talking about this thing called angle of elevation, the angle between the horizontal and a line of sight above the horizontal is called an angle of elevation. What I want you to do is I want you to stick your arm out directly in front of you. And then I want you to move your arm up as you look up at something. The angle subtended by the motion of your arm is the angle of elevation. And so specifically, here is that picture. That is, you're standing and you look up to a plane. The angle subtended by your movement of your eyes is the angle of elevation. The angle of depression is the angle between the horizontal and a line of sight below the horizontal. So specifically, if you look out and then you look down at something, the amount of angle that subtends from looking down is an angle of depression. And so if you consider that same picture I had before, the airplane, if you were the pilot and you were looking down at that person in this photo, the angle subtended by your eyes moving from the horizontal down, that is the angle of depression. Now, something that I want to observe at this point, that is, we have an angle of elevation, this. We have an angle of depression, this. Now, in terms of all of our pictures, we're going to create a right triangle, and the right triangle is going to look like this. But if you remember geometry, what happens is that this angle here and this angle here are actually exactly the same. And so in terms of our images, angle of depression and angle of elevation are almost exactly the same. Actually, they are exactly the same depending upon the viewer. And so recognize that that's true, so just be careful in these setups. So let's try one. A surveyor measures the distance from the base of the tree to a location away from the tree and measures the angle of elevation from this location to the top of the tree. They find that the horizontal distance from the tree is 48 feet and the angle of elevation to the top of the tree is 65 degrees. We want to know what is the height of the tree. So let's sketch a picture. So let me draw a bad tree. Like I said, it was going to be a bad tree. There we are. We're going to call this the base. So this person, they walk away from it. And so what's the distance that they walk away from the tree? The distance they walk away from the tree is 48 feet. And that we're going to assume, for the sake of ease, that what's really happening is we're going to assume this is where our right angle is. So we're going to assume a right angle, and we're going to assume that this distance to the person is 48 feet. The angle subtended is going to look like this. And so this is the theta that we're given. Specifically, that angle measurement is 65 degrees, and the base of that triangle is 48 feet. Well, if we want to know what is the height of the tree, since we have this angle 65, this is really the opposite side, right? And so if I have adjacent and opposite, well, I'm thinking that tangent of 65 degrees is the exact same thing as the opposite side over the adjacent side, but I don't know what the opposite side is, but I do know that the adjacent side is 45 feet. Then I can just solve for the opposite side, multiply both sides by 45. Then I get that the opposite side, or the height of the tree, is equal to 45 times tangent of 65 degrees. And so 45 times tangent of 65 degrees, I didn't write down where to round to. And so let's round to 2 decimal places. That is 96.50 feet. If we needed to round slightly differently, we could deal with that, but I claim this is about how tall that tree should be. Let's try another. A building that is 300 feet tall. So we have a building. Just going to put a couple windows up top and a door at the bottom. If nothing else, just always draw bad pictures and then you can laugh at it. So this building is 300 feet tall. And specifically, it casts a shadow that's 60 feet long. Okay, so let's see what we get. So I'm going to go ahead and draw in the sun. And so if here's the sun creates a shadow. And so what happens is that shadow comes down here. We're assuming that our right angle is here, and that height is 300. Well, if the shadow is 60 feet, we want to know what is the angle of elevation of the sun. Well, that's theta. And so I notice that this is the opposite side of that theta. This is the adjacent side of that theta. And so then tangent of theta is going to be equal to 300 divided by 60. You could reduce the 300 divided by 60 if you so desire. That's really 5, right? And so since that's 5, at this point I have that tangent of theta is equal to 5, but if I'm trying to find that angle theta, that's really going to be tangent inverse of both sides, where theta is then equal to tangent inverse of 5. And I get that this is approximately, and I'm just going to round it to 2 decimal places again, 78.69 degrees. And so I claim that that's our angle of elevation. Once again, remember that if we were looking at the base of the building and we look up towards the sun, that's the angle of elevation.